This slide shows 4 examples of priors on theta. The first one, for example, is the uniform distribution on all possible parameters. So this one wouldn't put any inductive bias. It does not prefer any solutions for theta over others. And this actually turns out to be maximum likelihood estimation. So you could say that maximum likelihood estimation is actually a special case of this posterior analysis. The other 3 options put some inductive bias on theta. In particular, you can observe that all of them are centered around 0.5, and they are centered around with a different width. So this means we're more or less certain that 0.5 is actually the real solution, or that the real solution is in an interval, small interval around 0.5. Okay, so how do we choose our prior to look like this? And the answer is, again, that we would like to ease the computations, okay? So we're adding this extra term, and we would like to avoid that the computations get much more expensive and much more complicated. And this will be the driving factor for choosing an appropriate prior for our specific model, in our case, the coin flip. We're trying to find a distribution that will make our lives easier in subsequent calculations. And it turns out that whenever you're looking for a prior for a parameter that directly corresponds to a probability, like in our case the theta corresponds to the probability of tails showing up in a coin flip, there is indeed such a prior that fits well. And this prior is the beta distribution. And the beta distribution is depicted here. This is the PDF of the beta distribution. And it looks a bit complicated at first glance, but at second glance we recognize terms that we've seen before. Specifically, these 2 terms depending on theta, they look a lot like the likelihood we've seen previously, except that the number of tails and the number of heads in the exponents have been replaced with a-1 and b-1. Moreover, you just have this normalizing constant consisting of gamma functions. The gamma function itself is a bit complicated. What you need to remember about it is that it is a natural extension of the factorial function. So the connection is that the gamma function evaluated at some natural number n is actually the same as the factorial of n-1. The difference is that you can also evaluate the gamma function at values between integers. So the gamma function of 1.5 is well defined, whereas the factorial of 1.5 is not defined. Okay? And whenever you have such a prior that has a similar functional form as the likelihood, and they fit well together, you talk about so-called conjugate prior. And the beta distribution is a conjugate prior for the likelihood of our coin flip experiment, okay? And the interpretation is the following. Without seeing any data, we have a feeling about what the outcomes of our coin flip sequence is going to be. And if we were to do a plus b minus 2 coin flips, then we can choose the prior such that we would expect about a minus 1 of those a plus b minus 2 coin flips to show up tails, and b minus 1, the remaining b minus 1 flips would show up heads. And for example, if you were to assume that the coin is probably unbiased, you would choose a and b to be equal, and the more certain you are about it, the higher you would choose a and b. And here we can see beta PDFs for different choices of A and B. And I should point out that you've already seen beta PDFs, namely on a previous slide where I was showing possible choices for priors, and these were actually all already beta PDFs or beta distributions. A very nice feature of the beta distribution is that it generalizes the uniform distribution. Namely, if you choose A and B, both equal to 1, like in the top left corner here, what you get back is the uniform distribution. But the other 3 plots on these slides are also interesting to look at, because they show what happens if you choose A and B not to be equal. So remember, on this previous slide, the priors were all centered around 0.5 with a different width. And the difference here was that A and B were equal, but were displayed at different values. And now A and B can be different. And what happens is that you get a bias towards tails or towards heads, or a probability that favors tails or heads, depending on whether you choose A or B to be higher. And another interesting case is if you choose A and B to be non-integers, like in this bottom right plot, where they were both chosen to be 0.1. And this favors the extreme solutions. The interpretation of A and B being kind of expected results gets a bit lost, but it gives you a lot of flexibility in modeling the prior distribution. Now we got to know the beta as a reasonable prior for our problem. And what we can do now is we can plug in everything we know into the formula for the posterior that we already derived, and that was this formula, if you recall that. And here we have this dependence on the likelihood and on the prior and also on the evidence, but we'll soon see that the evidence is not so important. Now let's recall what we know. We know that the likelihood takes on this form, and you may recall that we had something like theta to the third times 1 minus theta to the power of 7 for our specific sequence. And the reason why we're writing x here instead of theta is that theta is now a random variable, and a random variable takes on a specific value x. So x takes now the role of theta in the maximum likelihood estimation. And we've also decided that the prior is a beta distribution, so it takes on this form. Now, before we plug it in and keep on calculating and deriving new results, we will need to introduce some notation, and this notation is this sign down here, this symbol, and that's a proportional to symbol. It's actually quite simple. So if a function a of x is proportional to a function b of x, this is by definition the case if there exists a constant with respect to c, such that a of x is c times b of x. So what this means is the functions a of x and b of x are actually the same up to a constant. So b of x is always c times larger or smaller than a of x. Okay, c must not be 0. That's one thing, so c is not equal to 0. But this is the case here, because if we plug in the likelihood and the prior, we still have the evidence left, but the evidence, we can just erase it because it's constant with respect to x, as well as the normalizing constant of the beta distribution. And both of them are quite nasty, but the nice thing is, with the help of this proportional to sign, we can just erase them, because again, we're interested in the maximum of the posterior, and the position of the maximum doesn't change if I delete constants. Just the value of the maximum changes, not the position. And if we look at this last line here, we can also see why the beta distribution, or the conjugate prior in general, is so powerful, because this term actually looks like the likelihood, except that it has these correcting terms b minus 1 and a minus 1. So no matter how extreme t and h are, like in this case where we only flip the coin twice, you have this correcting term of a and b. So you're pulling the result away from these extreme marginal results like we got in the maximum likelihood case with too little data. And this is why conjugate priors are such a good choice as a prior, because they have exactly this effect. One more reason why we can get rid of these constants is that it's actually very easy to recover them if we ever need them. And to see that, let's look at an example. Suppose you have to calculate the integral over the real line of the function e to the minus x squared with respect to x. And that's actually analytically a very hard thing to do. But luckily we know the following. We know that if we integrate the function 1 over the square root of 2 pi times e to the minus x squared with respect to x. This is 1. Why is that the case? Well, the integrand here, this expression here, is the PDF of a standard normal or standard Gaussian distribution with zero mean and variance 1. And because it's a PDF, if we integrate over the entire real line, the result must be 1. But now we can pull out this constant 1 over the square root of 2 pi, and what we have is c times the integral we actually have to solve. So we can divide by this constant, and this immediately implies that we actually know the result of this integral, and it needs to be the square root of 2 pi, which is the inverse of the normalizing constant of this other PDF. And it turns out we can do the exact same thing in our case here. Why? Well, we know our posterior is proportional to this thing. And this expression is the PDF of a beta distribution up to its normalizing constant. Okay? So the only constant that we can insert here is the normalizing constant of the respective beta distribution. And so the constant that we need to fill in here, it must be this expression. There's no other way we can find a constant that lets the right-hand side integrate to 1. And it needs to integrate to 1 so that we can exchange the proportional to sign with an equal sign. Okay? And this is a very nice, very convenient trick that you need to keep in mind. Whenever you're supposed to solve a hard integral, try to look at it and try to find if it looks like a PDF. And if it looks like a PDF, you can easily reverse engineer the normalizing constant of this PDF, and you can then easily solve the integral. An immediate and very nice consequence of this reverse engineering trick is that we can easily determine the distribution of our posterior. And because of this reverse engineering trick, we know that our posterior needs to be a beta distribution, and we even know the parameters. And now, just like in the maximum likelihood case, where we maximize the likelihood, we can now set out to maximize the posterior. And if we do that, it's again the exact same calculations, taking the derivative of this beta distribution and so on. We will skip these exact steps. What you end up with is another point estimate, and this is the maximum a posteriori point estimate. And if you compare this maximum a posteriori point estimate to the maximum likelihood estimate, you see that it's actually quite similar. So let's recall that the maximum likelihood estimate was the number of tails over the total number of flips. And this term kind of pops up in the maximum a posteriori again, except that it's corrected with our prior belief. And now this maximum a posteriori estimate can be interpreted as the best guess for theta under the IID assumption on the data, so that's the same as in the maximum likelihood setting, and the additional assumption of our prior belief. So given that we believe in what we encoded in the prior, the maximum a posteriori estimate becomes the best guess. Now, notice something very interesting. The posterior actually works very intuitively. What does it do? If you have very little data, like in our second experiment where we only had 2 coin flips, the effect of the prior is much stronger. So if t and h in this expression here are very small, the effect of a and b is very large. On the other hand, for a fixed a and b, if I do sufficiently many coin flips, if I do 1,000,000 coin flips, then the effect of a and b is almost negligible, and I get very close to the maximum likelihood estimate. And that's very intuitive, because in the low data regime, the prior prevents overfitting, whereas if I have a lot of reliable information from the random process, I don't really need the prior information anymore. I can get all of it from data. And that's a very convenient way the maximum a posteriori estimate works.